Well, first of all, I would like to thank the organizers for the invitation to be here today. It's been already a great conference. And with this time slot, I would like to tell you about a new result that was mostly carried out by my PhD student, Hannah Seabrook, under my supervision and in collaboration with Paul Skripczyk and Fabio Costa. And it's about closing the closed lab loophole in device-independent tests of indefinite causality. Now, since this was a bit of a change of topic from the previous talks, I thought I would start with a bit of an introduction to the problem, so to indefinite causality and to device-independent tests of indefinite causality. So I thought I would start from something that everyone here should be fairly familiar with, which is Bell's inequalities and Bell's theorem. Now, you will have probably heard sentences like, Bell's theorem showed that nature is incompatible with local realism. Now, this is one of the strengths of Bell's theorem, that it enables us to draw conclusions about properties of nature rather than of theories that we use to describe it. And this is linked to one of its most peculiar aspects, which is its device independency. So Bell's theorem is a device-independent test in the sense that violating Bell inequalities reveals properties of nature, for example, directly from observed statistics, rather without having to make any assumption about the internal functioning of the devices that were used to perform the experiment. Now, this is possibly one of the most important properties of Bell tests, and it has been pivotal both for the foundations of physics, really to be able to draw conclusions about properties of nature, but also for practical tasks. For example, think of practical tasks involving untrusted devices like device-independent cryptography and self-testing. Miguel has spoken a little bit about those topics yesterday in his talk. Okay, so now, slight change of topic, indefinite causality. Now, this is the new property of nature that we want to be able to certify through some possibly device-independent tests. Now, in indefinite causality, what we typically, very loosely speaking, what people say is that, well, if you look at standard physics, even just like textbook quantum mechanics, that assumes a definite causal order of events. But in principle, quantum mechanics would allow for example, superposition of causal orders. So what do I mean with this? First of all, what do I mean with textbook quantum mechanics? When I say textbook quantum mechanics, I'm referring to, for example, the concepts of quantum circuits. Now, in quantum circuits, information is encoded into quantum states and time evolves under sequence of gates. So, for example, you will see those wires where implicitly it's assumed that time evolves from left to right, and you will apply those gates in a sequence. Right? And this is obviously a very useful framework because it's an intuitive way of representing computation, but also because some of the most powerful and best known quantum algorithms are written in this language. However, this is not the most general way in which you could write, for example, quantum computation. Think of, for example, say you have two gates, two quantum operations, O1 and O2, and say you want to apply them on the same system, a target system, for example. And suppose that you use a separate quantum system, let's call it a control system, that decides the order. So, for example, if your control system is in a state 0, then you're going to apply operation O1 first. And if it's in a state 1, then you will apply O2 first. Now, obviously, because this second system is a quantum system as well, you don't necessarily just have to apply to have it in a state 0 or 1, but you can also have it in a quantum superposition of the two. This would give rise to a quantum superposition of the different order of applications of operation 1 and operation 2. Okay? This is the simplest example of an indefinite causal order. It's called the quantum switch. And obviously, everything I said for the case of two-party can be generalized to more parties. But also, this is kind of just the tip of the iceberg, really. There are many more, possibly more interesting quantum causal processes that can be studied. However, for the scope of this talk, I'm not going to need anything beyond this simple quantum switch, so I'm not going to introduce more processes. But so indefinite causality has been shown experimentally, this quantum switch, for example. We have seen it in a number of experiments, mostly within a photonic system, but in a variety of degrees of freedom, for example, and also varying the number of parties, for example. Likewise, we have also seen a lot of papers coming up, both experimentally and theoretically, showing advantages with the use of indefinite causal structure. For example, we've seen advantages in quantum computation complexity, quantum communication complexity, quantum metrology. Now, all of these advantages have been very much device dependent. So as such, you might wonder, okay, could we do something just like in non-locality? You know, we can devise tests that have this, you know, dimension of device independency. Could we do something similar also in indefinite causality? Well, in principle, the answer one would expect could be yes, because we do have the notion of causal inequalities in indefinite causality, which can be understood as somewhat the analogous of what Bell inequalities are in non-locality, but for indefinite causality. So they were proposed, for example, the first version in 2012, and since then we had bipartite causal inequalities, tripartite one, full characterization of the polytopes for the simplest causal inequalities. But in these 14 years, we have still not found a physical process that could be implemented, for example, in a lab that would give rise to violation of those inequalities. So we wouldn't be able to see any of this experimentally, let alone build something out of that. This is the reason why more recently a new type of inequalities was proposed, typically lately referred to as causal local inequalities, where they took the quantum switch, so this example that I was telling you we know how to build in a lab, and they mixed it with some properties from non-locality to give rise to some kind of combined tests of non-locality and indefinite causality that can be performed in a device-independent way. Now, this was really cool because finally it opened the way for some experimental certification of device-independent tests of indefinite causal order. And in fact, we have seen them. We have seen recently a bunch of experiments that started to show some initial violation of those inequalities. Now, however, the problem is, as you can see, for example, already from the title of this one, but everything I said applies also to the other two, these are not quite experimental demonstration of device-independent tests of indefinite causality. And the reason is, well, in short, one could say it's because they don't close all the loopholes, so they're not loophole-free. Now, if I say that, however, it might sound like, okay, so what? The first tests of Bell inequalities weren't loophole-free either. We will eventually get there. Well, but it's a little bit different because Bell loopholes could, in principle, be closed. Of course, there are some loopholes that can be closed, but they very often sound more like conspiracies than real loopholes. Whereas in this case, there are some loopholes that they fundamentally cannot be closed in the way that the experiments, the tests are designed at the moment. And they're not conspiracies. They're things that can definitely occur with the very same setups that you use to violate normal causal inequalities or causal local inequalities. So what are these assumptions? Well, this assumption is the closed laboratories assumption. So the idea is that parties can only communicate via this target system. So they can only basically open the door of the lab, get this target system in, perform an operation, open the door, let the system out. This is the only interaction that they can have with the external world. So they cannot send, for example, multiple signal or anything like this. This is done to avoid the possibility of two-way signaling. And I will tell you more about this in a couple of slides. Now, the problem with that is that this is an assumption that is inherently device dependent. It requires the trust in the devices. You have to trust that those devices will not make two-way signaling, for example, that they will only ever interact with the external world through this one target system. And directly testing this assumption would project actually onto a definite causal order. So then any tests of indefinite causal order would not be possible because you would have projected onto a definite causal order. So in this talk, what I will show you is how we embed a test of closed laboratories directly into an existing device-independent ICO protocol. And I will need to add some minimal extra components that I will discuss. But with those minimal extra components, then the closed lab assumption become an operationally testable feature of the lab. Okay, so this was everything I wanted to say for kind of like a bit of background on indefinite causality and the motivation behind this work. Just to give you an idea of what to expect next, I'm gonna talk a little bit more in depth about this closed lab assumption, both why it's necessary and also the device dependence of this assumption. And then I'm going to move on to the main result, which is this integrated test for indefinite causality and closed labs. And finally, I'm going to summarize and talk about next steps. So let's start with this necessity side. Now, the necessity of the closed lab assumption is because of what follows. If you look at a classical space-time data alone, you will not be able to distinguish if you have an indefinite causal order process or a two-way signaling. What do I mean with this two? Now, an indefinite causal order process, as I was telling you before, for example, in the case of the quantum switch, is a scenario where you have two parties, A and B, for example, and you have that either A signals to B or B signals to A, and this happens in a quantum superposition of these two. So you have a quantum superposition of two one-way signaling, okay? Instead, in the case of two-way signaling, what you have is that you have both signaling from A to B and signaling from B to A, okay? Now, you might think, okay, so then we could just use classical inputs and outputs, and in that way, we would automatically be able to verify this closed lab assumption, because if any party was trying to slip extra information, we would detect it. Well, that won't work, because if you try to extract classical information during the process, this reveals some timing information. And once you reveal the timing information, you would project onto a definite causal order. And so, because of this, you can't simply do that. So you must remain coherent all throughout the process. This means, however, as a side effect, that any device-independent test of indefinite causal order that you could conceive must place classical inputs and outputs in a space-time configuration that in turn ends up being also compatible with two-way signaling. Just to say this also from a different perspective, maybe the people that might be more familiar with like polytopes and non-locality. So in non-locality, everyone will have seen this type of picture. This was taken by in this review from Nicolas Brunner and co-authors. There you have that the local set is strictly contained in the non-signaling set, and that the quantum non-local correlation can violate locality while still respecting no signaling. And so this is why you can perform tests, a device-independent test where you certify quantum non-local correlations. In the case of indefinite causality instead, what you have is that you have those polytopes that are like the one-way signaling. This is the one-way signaling from Alice to Bob and the one-way signaling from Bob to Alice. And then you have the definite causal order set, which is just a convex mixture of those. So anything what is not a definite causal order will lay outside this polytope, but it ends up actually laying within the polytope of two-way signaling. And so to violate a definite causal order, correlation must lie outside this convex hull of one-way signaling, but they enter the region of this two-way signaling, okay? So, then about the device dependence, the problem with device dependence of this test. Well, you can simply just imagine it like a device-independent cryptography scenario. Imagine, for example, that your goal was to certify an indefinite causal order to achieve some advantage. I'm not going to now detail on what the advantage should be, but imagine just that if you could certify it device independently, you would have an advantage. And so imagine that you have some trusted parties that buy some devices from a manufacturer who is a malicious manufacturer that actually wants to cheat at this game. Now, this malicious manufacturer would potentially promise closed labs to the trusted parties, but actually secretly giving them devices that allow two-way signaling. So because the parties wouldn't be able to test the closed lab within the run, otherwise they would destroy the indefinite causal order, they would violate a causal inequality or a causal local inequality, but actually not because they had indefinite causal order. They would simply violate it because they had two-way signaling, okay? So this is the problem and why this is inherently device dependent. So how do we attempt to solve this? To be able to tell you about what we are doing, I need to just do one extra step and tell you about this, an example, an instance of a causal local inequality, which is this VBC inequality from the authors van der Lugt, Barrett, and Kiribella. So in this inequality works as follows. You have this a quantum switch, just like the one that I presented you before. You have two parties, A and B, inside this switch with classical inputs X and Y and classical outputs A and B, respectively. And then you have a party C at the end that performs operation on the control system, for example, projecting it onto a diagonal basis or something like this, whose inputs are Z and outputs are C. And then you have a space-like separated party D with input W and output D. You're going to send an entangled pair, part through the switch and part through this party D. When you go through the switch, this is going to then be the control system. And then you send a generic state rho as your target system. Okay? Now they consider this combined framework called DRF, D for defined causal order among A, B, and C. R as relativistic causality, so no signaling from this bunch to D, and to and from D. And then F as free local intervention, so independent inputs, similarly to what you would have in Bell, for example. So under this DRF assumption, they showed in their paper that all classical causal models will satisfy this inequality. Now, this inequality can be understood as follows. Those first two terms can be maximized either by a quantum switch, for example, because you would have, this term would give you enough, this term would give you enough, so you would have one, or by a fully definite causal order, for example, because one of the two would give you one, so you would have either one-way signaling from Alice to Bob or one-way signaling from Bob to Alice. But the second term instead, this is the CHSH term, and a CHSH inequality is played between the party C and the party D, where C, as I was just to remind you, was performing operation on this control system. And so this can only be maximized when you have actually an entanglement between the control system here and this party here. And so this turns out to be maximized by an indefinite causal order. So an indefinite causal order will give you something that is above 7/4. Now the problem is that this is only true when the closed lab assumption is verified. So if the closed lab assumption does not hold, and so two-way signaling is allowed, actually the algebraic limit of this becomes 2. And so you might see a violation of this, so a number above 7/4, even though you didn't have an indefinite causal order, you just had two-way signaling. Now at the moment, none of the causal inequalities nor this causal local inequality deals with that. It's just an assumption that they say, okay, this should be respected, but they don't really give you any way to actually verify this. So the way in which we tried to tackle this was to embed tests of this closed lab assumption directly within this BBC framework. So the idea is the following. We have some assumptions, some operational assumptions. First of all, we have photonic signaling only. So labs are shielded so that only photons can carry information between them. For example, imagine some lead walls. Second assumption is that we will have some beam splitters at the input and output of this of the labs. And we recombine them in the system, and then we measure it through these detectors. And we assume that these elements are passive and do not signal. So this is a device-dependent assumption as such. And then we have a timing constraint, so this clock here. So we assume that the inputs are chosen at a time t0 equals 0, and that the outputs are read before any light speed round trip is possible. So at time t1, that is going to be between tau and 2 tau, where tau is the time that it takes for light to travel between A and B, or vice versa. Now, under this assumption, then we build this adapted test for combined testing closed lab assumption and indefinite causal order. If we had indefinite causal order, we would have that each device is only allowed to interact with the target system at most once. Instead, just to remind you, if you had two-way signaling, the device could interact with the target system multiple times. So then a test of closed labs simply would ask something like, did any device interact with the photonic signals more than once? Now, to certify that, what we do is that we monitor the reflected photons out of these extra beam splitters that I was showing you we added. So in each run, we record whether a detector clicked at one of two time windows, A T0 or 1, and B T0 or 1. we will have that 0 is no click and 1 is click. And then we define the quantity n, which is the sum of AT0 plus AT1 plus BT0 plus BT1 as the total number of detector clicks in that run. Then what we do is that we consider the two scenarios where n equal to 0, so all photons were transmitted, none of the extra detector clicked, and so that run is going to be used just for the VBC inequality, okay? Instead, when n is larger or equal to 1, then it means that at least one photon was reflected, and therefore we're going to use this to gain some space-time information about the signal propagating in the system. So therefore, the VBC inequalities now have to be evaluated but conditioned on n equals 0, whereas the runs for n larger than 0 are going to be used to test this closed lab assumption. So the test looks like this. You're going to violate, this is pretty much the VBC inequality, just conditioned on n, subject to this constraint. So as I said, the top part is nothing new. This is just VBC inequality, and violating this will rule out a definite causal order. So it will tell you, you either have indefinite causal order or you have two-way signaling. Instead, the bottom part is the one that for a fixed D, where I remind you D was the outcome of Dave, the space-like separated party, when W was equal to 0, then each party is only allowed to see one click, either early, if they acted first, or late, if they acted second. But you can't have both, so the product of this has to be 0, so at least one of the two has to be 0, okay? Otherwise, you will classify it as a two-way signaling. So if it's satisfied, it will tell you that the process is in indefinite causal order. If not, it will tell you that two-way signaling might have occurred. So in that sense, it is a necessary condition, but not, a sufficient condition, but not necessary. So you might wonder, why is it okay to only look at W equals 0? Well, if W is equal to 0, D measures in the Z basis. So at the switch, you will have a definite causal order. So you are able to see some correlations between the outcomes and D and AET0, AT1, and so on. But instead, when W is equal 1, D will measure in the X basis. So you have an indefinite causal order. And so you will not be able to see clear correlation between those quantities. And so this is the reason why we focused on W equals 0. But then you might be wondering, okay, but how is this fair? I mean, are you post-selecting on the cases where W is equal to 0? Well, no, because signaling between A and B is determined by the causal process occurring in the switch, whereas the party D is space-like separated from them. So this means that the underlying process that occurs in the switch is going to be independent of W, independent of the input of the space-like separated party. And so the closed lab constraint, if it holds for W equals 0, must automatically hold for W equal 1 because they're space-like separated. Okay, so, everything clear, but nevertheless, not quite happy because these are not really device-independent assumptions. And it's true. So the photonic isolation can be enforced with some shielded enclosure. You might assume properties of just particle physics, and you might say, okay, perhaps, fine. The timing, well, timing relies on trusted clocks. You have to trust that the clocks are telling you the right thing. So again, not so device independent, but actually clocks and timing is already assumed in Bell, so perhaps you might be comfortable with that. Likewise, also in Bell, you're, for example, assuming the validity of general relativity. So you are making, even in Bell, you are making some level of theory-dependent assumption, device-dependent assumption. But here, obviously, we bring the line a little bit further because we have also these extra beam splitter and detectors that they must be calibrated, and you must trust, for example, that beam splitters are no signaling. Now, we tried to do it as a kind of minimal set of extra operational devices. For example, beam splitters are see-through, and you could reasonably assume that they wouldn't be able to perform signaling because they're not birefringent materials, but obviously this is a very device-dependent assumption. So this is possibly the biggest weakness of this. But at the same time, we don't make any assumptions about the internal working of the black box devices introducing the correlations. So at least we don't hide under the carpet the closed lab assumption as you would do instead in other tests of indefinite causal order. So with this, I kind of said everything what I wanted to say. So just to summarize, there are existing indefinite causal order certification range from device dependent to semi-device independent to fully device independent. Now the device dependent and semi-device independent require, however, the characterization of the quantum operations prior to performing the test. The fully device independent schemes avoid this, but in a sense hide under the carpet the fact that they're relying on an assumption that is very device dependent and as such at the moment cannot be tested within the experiment. In this work, we aim to keep the strengths of fully device independent tests, but we wanted to move trust away from the adversarial devices that you would buy from this manufacturer. And instead, the trust is placed in some testable lab infrastructure that obviously makes the test more device dependent, but perhaps one might be comfortable with accepting that we just might need to move the line a little bit, the bar of what is acceptable in terms of device dependency, if we ever want to be able to perform device independent tests of indefinite causality, or perhaps you want to draw the opposite conclusion that we might not be able to perform device independent tests of indefinite causality after all, in the same way as we talk about device independency in Bell. So next steps. Well, extension to other causal inequalities. This is actually the most straightforward part. Pretty much everything I said can be kind of straightforwardly applied to other causal inequalities, although the conclusions that you would draw from this are kind of interesting in terms of whether actually one would classify them as two-way signaling. Effect of practical limitations, for example, imperfect detectors. This is actually a more challenging one already. We are working on this, and it is not so straightforward. So we're trying, for example, to see what sort of efficiencies one would be able to tolerate. And likewise, also perhaps if you don't want to rely on these clocks and you want to rely on click statistics alone, we are also working on that, but we're showing that this could be done in principle, but it will come at the cost of introducing some theory dependence. So with this, I tell you everything I want to say, so thank you for your attention.
Okay, do you have questions?
Well, thanks for the nice talk. I was a bit surprised. I didn't know that you could violate causal inequalities. So I stopped in 2022 and this nice result from 2023. But my question is like, so this closed labs assumption, actually you need this in basically any scenario that it's time-like, right? So like if you move to, you have Bell scenarios with communication, like this temporal Bell scenarios, or like Leggett Garg, I guess, or these sort of things. So can you adapt this construction to other temporal scenarios as well?
I guess the problem is that in that case, you're considering no signaling between Alice and Bob, for example, right?
Like, no, like you do allow for time-like correlations, right? So like Alice does something, then Bob does something, and so on. But you have to assume that you have like one-way communication. So you have many scenarios where you have to assume that. So you think you could adapt?
I don't think so, because at the moment, all of the possible correlations that would enable a quantum superposition between the two one-way signalings would also allow two-way signaling. So any sort of correlations that you would observe within with an indefinite causal order, so that go beyond a definite causal order. So having just a one-way signaling that can be told apart easily from a two-way signaling. And so I guess that would be more close to perhaps those sort of tests.
Okay, yeah.
But if you want to go beyond that and you want to have a quantum superposition of the two, then you automatically would have clicks at 2 times, for example. And so in terms of classical correlation, you would end up in the same.
Yeah, thanks.
More questions?
So thanks for the talk. And my question is kind of related with Raphael. And this loophole, the closed labs, is also a loophole in the first type of indefinite causal order inequalities as well. It's not about this causal one.
No. That's what I was trying to say at the end, but maybe I was going a bit fast. So the original versions of causal inequalities, they were proposed 14 years ago, and we knew mathematical ways of violating them, but for example, we didn't know some physical ways that you could implement in a lab. But for example, in 2023, there was this paper from Bex, Branciard, and Oreshkov, where they showed a circuit that could be used to violate a tripartite causal inequality. And if you apply this same verification that we do to their test, actually would say that there was a two-way signaling there. But in that case, it's because they have three parties, A, B, and C actually is doing C dagger, C. So in that sense, it goes back to the lab of the third party twice. And so that becomes hard to tell apart from two-way signaling, because there are schemes. For example, there was this paper from Del Santo and Dakic where they had this two-way signaling with one particle, where they have two parties. You create a quantum superposition of going through both. And then depending on whether it comes out of one port or the other port of the splitter, you either go back through party A or through party B. So there is no indefinite causal order, but you nevertheless can do two-way signaling. And as it turns out, that is very, very hard to tell apart from a quantum switch, for example. And the only way you can do it is by observing the timing in the correlations, for example. And so this is why, for example, that is a scenario where it's hard to tell apart from the switch, but in principle, it could be done with clocks. But the only physical process that we know would violate the standard causal inequalities, that one wouldn't even pass this test. So that one would even be certified as two-way signaling, actually, because of the fact that you have to go twice through the lab C. So it's even worse, perhaps.
Any more questions?
So I'm not so familiar with these things. I work more on the device and things. So we have these pictures like the one you took from the paper by Nicolas Bernard and the others. And now you were trying to make an analogy with your system. So if you can go to the figure, you were saying that, okay, the problem is that beyond your polytope, things are two-way signaling, no? And this is why okay, so I understand that somehow you want to exclude the explanation through two-way signaling, no?
So yeah, we want to say we don't have a definite causal order.
But you are not well, where are you in the picture, let's say?
Yeah.
This may be a question of, can you formalize sets or I don't know, like...
yes, we are out of the DCO, but within the two-way signaling.
But you want to, I thought that you wanted to avoid the two-way signaling explanation.
Exactly. And so this was the part where I was saying this is why we wouldn't be able to, from this alone, from statistic alone, we couldn't do it.
Exactly.
And this is why,
So now you introduce something and some of these picture changes?
So now we introduce these extra tests where we look at the timing information as well. So we add these extra components that are not included in standard causal inequalities and causal local inequalities. And we look at this timing information and we try to rule out all of the cases where information went back. And so this is why by adding these extra conditions, then we try to rule out.
I understand. So my question is, can you still understand in terms of nice figures and sets where you are now at the moment, or maybe a question. Okay, there's a coffee break, right?
Yeah, maybe let's talk reals. Let's.
Okay, so let's then go for the coffee break, and thanks, Giulia, again.
Thank you.